Thank you. Thank you for inviting me. So this is joint work with Jenna, Pamela, Catherine, and Chinchen. So let me just get started to tell you like briefly the background of why this is something interesting to look at. So because I only have 25 minutes, so I'm not going to go into detail. But if you're interested, actually, Tom Havazin and Theodore has like papers on talking about why this is important. So you can actually see that it is related to something called partition algebra and a symmetric group. And so that's like a throughout duality to tell you like the relation between these two things. And if you're not familiar with partition algebra, that's okay. You can always like look at the paper and see what that is. But like briefly speaking, it's just some sort of these diagrams. And then so your algebra, the elements are these diagrams, and you're talking about how you are going to do the multiplication together and create another diagram. And then sometimes you will have a coefficient in front of it. So that's like something like this. So yeah, so that's kind of like a really quick background. And something interesting here is that if you look at the partition algebra, and then you will realize that the basis for the partition algebra is actually corresponding to some set partition. So you can count, like you can actually just count or compute the dimension of the partition algebra, and then you will see that that's the file number 2K. All right, so of course, different people have different interpretations of these, and also like looking at Vacillating Tableaux of different sort. So for example, there's something described in 1986 in an up-down, what we call Vacillating Tableau, but it described the irreducible representation of the symplectic group SPQK. And Richard-Stanley established the bijection between the complete matchings on 2K vertices and also the up-down tableau of empty shape and length 2K. And Sheila in the audience also extended Richard-Stanley's bijection to arbitrary shapes, providing a combinatorial proof of the Cauchy identity for the symplectic group. So later on, there's a group of people introduces something called a simplified Vacillating Tableau and gave a bijection between set partitions and Vacillating Tableau of empty shapes, which demonstrate the symmetry between the maximal crossing and maximal nesting in set partition. So the catch here is that like this object has like really rich representation theory and algebra behind it, and also it has a lot of like set partition and combinatorics that you can play with it. So for this talk, I'm basically going to tell you what is Vacillating Tableau, what are the identities that we proved it, and hopefully that would interest you to also look at our paper and see different bijections that we have discovered. All right, so for the definition, so if I fix a k, which is a non-negative integer, and also a positive integer, and an n Vacillating Tableau of a fixed shape lambda, and length 2K is a sequence of integer partitions. So you have some shapes here. And then, so the first shape is always one row shape. So you have the n. And then the last shape is kind of like the indexing of the shape of your n Vacillating Tableau. And then the reason it's called vacillating is actually this requirement that the half shape is in between the kind of like the integer shapes. And then they always differ by a size of 1. So this definition seems a little bit hard to understand the first time. So basically what's going on is that you start with a one row shape, you minus a box, add a box, minus a box, and so on and so forth until the last step you add a box. Then you get a Vacillating Tableau. To give you a more concrete example, you can start with, say, for example, n equals to 6. You have a one row shape, just 6. And then what you do is that you want to minus a box in this case, and also keep partition. So that's only one box that you can do. So you have a shape 5. Now you have a choice to add again. So add a box. So you have two choices. You can either add on the first row or the second row, depending on your mood. So say, for example, today I want to add to the second row still a partition shape. I have a partition shape of +1. And then now minus plus, so I can do a minus sign again. And then now I have two choices. I can remove this or remove this and still get a shape. So say, for example, I'll remove that, I get 4-1 and add again. And then now I can add 3 choices. I add this one, 4-2, and then do once more minus this shape. And then I have 4-1. Remember, the last step is always adding. So then you get this one and then 4-1-1. Okay, so there are many choices here. This is a particular choice that I made. And so here, this guy is actually a 6 Vacillating Tableaux of shape 4-1-1, which is the final shape. And then the length will be 6 because you see like you have 1, 2, 3, 4, 5, 6 starting with 0. Okay, so that's how we talk about the shape. So lambda 0, lambda half, lambda 1, and so on and so forth. And one thing that you will notice is that all the integer shapes 0, 1, 2, 3, they are all with 6 boxes. So they are partition of 6. The half integers ones are always a partition of 5, which is just a lowercase. So if we look at the Young diagram, so basically all the shapes are just either 6 or 5. So we look at these two levels. So you can see that the 6 is here, and then 5, and so on and so forth. So you're actually oscillating between the two layers. And that is the reason why we call it a vacillating tableau. All right. So this, if we want to count by just like looking at this, is kind of hard to count how many vacillating tableaus are there. So we are going to draw a diagram in this way. So we start with 6, and then that's only one choice to go down. So that's 5. And then go back up, there are 2 choices. Go back down, 2 choices, and so on and so forth. So kind of expanding all the choices here. And now we want to count how many, right? So it's kind of like you have all these paths. You start with a 1, and then you have 1 choice. Each of them gives you 1, 1 here, and then you will have 2, 1, and so on and so forth. So you can count how many ways to go from the 1 row shape to a particular shape by just drawing this diagram. And then for each of them, you have some level here, so that corresponding to your K. And so this is just a notation to talk about the number of vacillating tableau of shape lambda, and then K is these Ks. Okay, so basically it's like length to K. All right, so what do we know about all these numbers? So in 2004, there's a theorem saying that if you have the number of vacillating tableau of length 2K and the final shape is lambda, if you square them and add them up, basically what you will get out would be the Bell number of 2K. And then, so you can see the difference here. If you just change one of the MK lambda to a standard Young tableau here, then you will get n to the power k here. And that's a very nice combinatorial description of what these are. So basically, there's a deletion insertion bijection that if you give me a length k integer sequence where the entries are from 1 to n, then you can actually give me a pair of standard Young tableau and also vacillating tableau of this desired lambda. Okay, so there's some formulas here. And then in 2007, there's another one is saying that, okay, if I just want the final shape to be 1 row, okay, and then so what are these just m, k, n? So basically they are the Bell number of k. So it's the number of subpartitions with k objects. Here is actually in 1998 with a much more generalized result, because here you can see that n has to be bigger than or equal to 2k, but here you can also work with any n and k bigger than or equal to 1. So it says that if you have a 1 row shape even your n is not bigger than or equal to 2k, you can actually write this as a sum of the number of subpartition of k into j non-empty blocks. So that's all this skj, right? And then you sum them up. So basically, if you know, it's like the Stirling number of the second kind. And then in 2023, there's another method using the growth diagram and realize that, oh, instead of one row shape, however, I want the last shape to be one column. If that's the case, that's also a very nice formula. You just add up this Stirling numbers. So of the second kind that you just like add skn minus 1 plus skn. And then add them up. And also here, nk can be any positive integers. So that's a very, very nice theorem as well. So you can see that like just studying these numbers have been quite active in the literature. So that's why we want to like discover more identities here. So now, hopefully now at least you remember what is Vacillating Tableaux and also the M numbers. And here, what I'm going to tell you is another simplification, which we call it a simplified Vacillating Tableau. So everything basically the same. The only difference is that every time when you are going from one shape to the other shape, you can, so here the first row has to be equal. So this two shape has to be equal, but then afterwards it's either equal or plus a box. So we say stay the same or add a box, stay the same or minus a box, and so on and so forth. And the last one is either stay the same or add a box. Basically, what you are saying is that I allowed you every time either to, or you just do nothing. So that's the simplified Vacillating Tableau. Now, of course, why do you call it simplified at all, right? So you can enjoy the cute doggies. All right, so remember this example that I talked about here. And then so if I remove the first row, then I will have these shapes. So empty shape, 1, 1, 2, 1, 1, 1. And you can check whether it is a simplified Vacillating Tableau of the requirement that I defined it. So here you see that it's actually equal for the first two shapes. And then you add a box, stay the same, add a box, and then minus a box and add a box, right? So even if I remove the first row, I still satisfy the requirement here. So that's the reason why it is actually a simplified Vacillating Tableau. So from here to here is very simple. You just remove the first row shape. So here 4, 1, 1 becomes 1, 1 because that's the last thing. So that's the reason why we call it simplified Vacillating Tableau, because it kind of can be retrieved by removing the first row, but that's kind of a catch, and you will see why. So here is a diagram that depicts the simplified Vacillating Tableau. So you start from an empty shape and you can choose the length that you want to and then go to a certain shape by either doing, so the first step has to be equal. Here you do nothing or add a box, do nothing, remove a box, right? Or here, if you start from here, you do nothing or you remove a box and so on. So that's similar diagram, but for simplified Vacillating Tableau. And now if you do exactly the same game and try to count how many simplified Vacillating Tableau, and you will realize that, hey, I can do exactly the same math here, starting with 1 and so on and so forth. And in this case, we call it GK mu here, just to count the simplified version. Now, if you remember our previous diagram, when my lambda is a partition of 6, you can see that these two guys are exactly the same thing. So here, when I say lambda star, I'm just saying that the lambda, getting from this lambda by removing the first row. So that's what this notation is. And you can see that they are actually equal when lambda is actually at least 2k. In this case, my lambda here, the size is 6 and my k is 3, right? So as long as your k is from 0 to 3, these two diagrams actually agrees. However, if you do more on the left-hand side and also the right-hand side, we start to see something different. So here you will see that the 1 here is missing from here. And so by kind of how you compute the next layer, you will realize that there's a bunch of things that are not the same. In general, if you count the number on the right-hand side is all, if you fix the shape here, is always greater than or equal to the left-hand side. So the simplified vacillating tableau has more options than the classical just vacillating tableau, unless n is bigger than or equal to 2k. So now to look at some nice identity, I'm going to split up into 2 cases. One, I'm looking at the even lengths. So basically, it's just like I always stop when k is an integer. So here we have a very nice formula and saying that, okay, if I just want to count the numbers on the right-hand side of the previous diagram, how am I going to tell you what these numbers are? Actually, these numbers are just the bk mu here, which is the number of subpartition of k with j marked up blocks. So this j here is the size of your mu times the number of standard Young tableau of the same shape of the mu that you chose here. Okay, so how do you actually prove something like this? So here, remember the GK mu represents the simplified Vacillating tableau. I use SVT here of the shape mu and then length 2k. And then here I have this pair, which is the number of subpartition of size k, right, 1 to k with the mu marked blocks. Okay, so I just translate that, and this is like the standard Young tableau of shape mu. And basically what I want to do is to set up a bijection between them. So how does that work here? So to start from the left-hand side to the right-hand side, I randomly choose a simplified vacillating tableau of some shape. So here I choose the shape 2, 1, and some length k here, k is 7. So you can see that length 2k, meaning that from 0, I'm going to 14 shapes here. So that's why k from 0 to 7. All right. So now I want to make a subpartition of 1 to k. So that's why it's 1 to 7 here. And so how do I do that? So first of all, with any shape here, I'm going to just like, this is 1, I'm going to write 1 here. And then if they are the same, I'm going to have a 1 here. And then the next box, I'm going to just move a 1 here. That's a box here that's empty. So I'm going to write down the k number here. So that's the 2. So far, so good. And then I'm going to do the 1, 2 here, going to do the 1, 2 here, an extra box. I'm going to put a 3 inside. And then now I have 2 boxes. What should I do here? Well, in this case, then you can do a kind of like a reverse of the RSK and see, okay, what is the number that would, that's a unique way to go from this shape to this shape using RSK. And you'll realize that 3 is the number that to be inserted in here, then you get here. Or in the other way, then you can think about 3 is the number that will bump out. And so this 3 will record it down here for our subpartition. And then the next step is 4. So we are going to make a arc from 3 to 4. Okay. And then now do the same game. 1, 2, put the 4 in because 4 is here. And then now I have a smaller shape. So again, I'm going to do RSK and see what number is bumped out. So in this case, you will realize that, oh, 1 is bumped out and I have the shape like 2, 4 here. So I'm going to have the 1 here. And the next step is 5. So I'm going to join the 1 and 5 together. And then now 2, 4 goes in, put the 5, and then move the same thing, move the same thing. And then you have the 6, so far so good. And then now you have a smaller shape doing the RSK, put the 4. And now you do the same thing. Even though it is in some arc, but it is in the end of the arc. So you can always choose this to start an arc. The next number is 7. So then I'm going to join 7 with the 4. And so you have this diagram here at the bottom. And so now that actually gives you a sub-partition. You have 1, 5 together, 2, 3, 4, 7, and also 6. So that gives you a sub-partition. And then you also have sort of a standard Young tableau, just that you have to standardize it. But these numbers will help you to mark all the blocks that you need. So you mark the blocks containing these numbers. So the 2, and then the 5, and also the 6. And so that's the mark the blocks. And afterwards, you can standardize. And you can check that this is going to give you a bijection, meaning that you can actually go back up. So that's how we prove this theorem. And then another thing that you can do is like, okay, what if I square it? Remember when you have that M here, that's something interesting going on. So like we are trying to, okay, well, what if I have the square of simplified Vacillating Tableaux, but let me just make it more general. I have different lengths of that and multiply them together and add them up. So what would I get? I will actually get the Bell number of K1 plus K2. So let me show you how we prove that, because this is actually quite simple. So basically the idea is that because all the Vacillating tableaux start with the empty shape. So you go from the empty shape to mu. Per actually asked some questions. So can only say anything similar to longest increasing subsequence as in classical RSK. Yes, because the identity may not show you, but there are things related to the longest increasing subsequence that you can kind of like talk about the first row of the shape. And there are something related in our other paper, but not this one. But if you want to know more, I can talk about it later. And anyway, so go back to here. We have this GK1 mu. So basically it's a simplified Vacillating tableau of length 2K1. And then from empty shape to the shape mu, right? And then so here, of course, you just do exactly the same thing. You have another one with empty shape to mu and then to K2. So if I want to multiply them, basically it's counting the number of pairs of them. And what I'm going to do is to flip the second one, move them together. And what do I get? Well, I actually get a vacillating tableau, simplified vacillating tableau with mu as one of the intermediate shape, and then from empty shape to empty shape, right? And so now I get this, right? So from empty shape to empty shape, so that's why it's shape 0, and then the length is 2K1 plus 2K2. And if you give me K1 and K2, I can easily just break it down by just looking at like where is the 2K1 mark and 2K2 mark. Wherever this shape is, that gives me the mu here, right? So that's good. Then I get back the original thing. So this is a bijection between pairs of SVT of different lengths to a SVT of shape, empty shape, and then length 2K1 plus 2K2. Right. So now, but that doesn't tell us about the Bell number, right? That only tells us this identity. But remember, we have this really nice formula that I just introduced to you guys, that I can just use this by putting the mu equals to empty shape. And then so now this is 0, and then that's the empty shape here. And we all know that F empty shape is just 1. So this basically is the Bell number. And that's it, right? So now you can ask different questions about this. You can ask, okay, well, what if I add all these things up together, right? So look at these guys. And then you're like, okay, if I add all the numbers in each row, right? What do I get? You get like 1, 2, 3, 7, and so on and so forth. And then if you just look at the integer ones, you will actually get a sequence in the OEIS. And so that is what we realized, that the GK, meaning that if you add them up, it is actually the number of symmetric partitions of minus K union K. What does that mean by symmetric partition? Well, any subpartition that if B is a block, even only if minus B is a block, then that's a symmetric partition. So to let you know like how this proof is like constructed, actually it's really similar to what we have, because like the goal is to like start with the simplify the vacillating tableau of these shape and then length, and I want to just like map to these sets, right? So remember, any SVT by the bijection, you can map it to a pair by the previous proof. So this is the previous proof that we have. And this is what we want to prove, which is the symmetric partition. So basically, I just need to translate my SVT to the symmetric partition here. And then, so if I give you a pair, something like this, then I have a way to construct it. So I know that my time is almost done, but let me just finish this proof and very quickly show you all the identities. So what you do is that you look at the marked blocks and then order them according to the marks. And then you have a, you just double your standard Young tableau that we know that is going to give you an involution by the RSK. And so with that, you can just say, okay, 1 is going to block 1, okay? And then 3 here, meaning that I am going to move block 6 here. And then 2, I'm going to move the 1, 5 here. So this is going to give you the involution to how to order these blocks. And then all these blocks at the second row, you just give a minus sign and then make them a block. And then afterwards, you have these things, which are going to give you part of the symmetric partitions. And then the 3, 4, 7 and minus 3, 4, minus 3, minus 4, minus 7 are the single blocks. So that's how you can link to from here to the symmetric partition, and you can actually easily go back. So that's how you prove things. So we have a bunch of results that I know that I don't have enough time to talk about, but let me just very quickly show you some of our results. So there's actually a slide. Oops, there's actually a slide of this. So I have talked about these 3, and actually there are more and more results. So what I did is actually, oops, sorry. So you can see that what we do is that instead of just multiplying another G, we multiply by another Schur function. Or if we change the G back to the M, what do we get on the right-hand side? So we are just like playing with all the combination of the G or the M and with the symmetric functions and so on and so forth. So basically we get a bunch of identities, and yeah, so I know that I don't have enough to talk about it, but just very quickly showcase what we have done. And this even works when the K is not a integer, even if this is a half integer, it will still works. All right, so I will stop here, and if you have any questions, just let me know.
Thanks, Anna. Questions from the audience? Okay, so if there are no questions, we're just gonna thank Anna again. And
actually, I think Sheila has a question.
Oh, Sheila, go ahead.
Yeah, sorry, I have one I do have one question. When you were showing the bijection where you you know, you do the RSK to map it to a standard tableau. And you were basically doing row insertion right there. Yes. Do you know what happens if instead of row insertion you did column insertion? Are the two related?
That we did not try. That's a very good question. We have done something similar to look at the dual RSK and basically like column insertion. and see how it is related, but we never think about using that in here. That's a really good question. I think
Yeah,
if
you
I
might
try
get a
something,
dual version of this.
right? That's what I'm going, like, that's my guess.
Okay. Yeah. Thanks.
Thank
Great
you.
talk.